This is a summary of a short talk given at Norwich University. The purpose of the talk is to get you to read a short note in the March 2010 edition of the American Mathematical Monthly. Kn is a graph with endpoints and an edge between each pair of points. It's called the complete graph. We're counting edge crossings and drawings of Kn on the plane or the sphere. Parity just means evenness or oddness. We're going to view these two drawings of K3 as the same, essentially because we can stretch one into the other. If you look at the drawing on the left, it divides the plane into two regions, a big infinite region on the outside and a small region on the inside. We're really going to view those two regions as the same. If it was on the sphere, then the infinite region wouldn't really be much more impressive than the inside region. This drawing of K3 is much different though. Here we have three regions instead of two, and some of the regions, a couple of them, are bounded not by pure edges but by parts of crossing edges. Here are a couple of different drawings of K4. The one on the left is planar. It divides the plane into four regions. The one on the right divides the plane into five regions, four of which are bounded in part by a crossing edge or part of a crossing edge. These two drawings of K4 we will view as the same. If you look at the first one on the left, the outside face or region is bounded by a 4 cycle. The one on the right also has a region bounded by a 4 cycle. It's highlighted in green. Here are a couple of different drawings of K5. The one on the left has 5 crossings. The one on the right has 3 crossings. Just a word about how we count crossings. If 3 edges go through the same point, we're really viewing that as 3 edge crossings. We're counting crossing pairs of edges. Here are a couple of other good drawings of K5. I'll say what that means in a minute. Okay, now here we have really the best possible drawing of K5. There is no drawing of K5 without edge crossings, so one is the best you can do in terms of smallest number of crossings. Inside of this drawing of K5, I've highlighted in red a K4, and the K4 isn't the best possible. We know you can draw a K4 without edge crossings, so that means if you're looking at the optimal or the best possible K5 drawings, you can't ignore less than optimal or suboptimal K4. So that raises the question, is there anything that you can ignore? So here's something that you can ignore. This will never be in a best possible drawing of any graph. You could always make a slight change without introducing any new crossings anywhere else in the graph. Okay, so we have a few situations, configurations that are not good. Especially focus on the one on the left. You have 2 crossing edges incident with the same vertex. So we'll say that's a violation of goodness at the vertex A. That won't happen. So in particular, that means if you have a crossing in a good drawing, you have to have at least 4 vertices to get that crossing. Okay, so now we're asking the question, can you have at least 2 crossings in a good drawing of K4? Well, we just mentioned that if you look at 3 vertices, there's no crossing. So I've drawn A, B, and C in black, and there's not going to be any crossings there. There's a 4th vertex, X. I may as well place it on the inside region. And now if there's going to be 2 or more crossings in a drawing of K4, they would both have to involve the vertex X. So we would have a violation of goodness at the vertex X. So now we want to know, can there be a good drawing of K5 with more than 5 crossings? And we also want to say something about the parity of the number of crossings in a good drawing of K5. Well, let's say you delete a vertex E and all of its incident edges. Then there are 4 vertices left. So we're looking at a K4. I've highlighted in green. If there's 4 vertices left, then there's at most one crossing if it's a good drawing. Okay, so if there's only 5 vertices that we could possibly delete, that means there's only at most 5 crossings in any good drawing of K5. If you have therefore an even number of crossings, that must mean less than 5. And so one of the K4s that we would look at must not have any crossings at all. So that means if you have a drawing of K5 with an even number of crossings, it would have to have something like this in it, the planar K4. So now we have the simple picture of a K4, 4 regions. So I'm going to put the 5th vertex, because we are after all looking at a K5. I'm going to put the 5th vertex, I'm going to call it U, and I'm going to put it on the outside. Now I want to know, how can I draw an edge from U to A? So I'm going to use the left version of the picture to see how I can draw an edge from U to A. Well, I've kind of doubled up the edges incident with A because I can't cross those if I'm drawing an edge from U to A. If I crossed an edge incident with A, it would be a violation of goodness at the vertex A. So the only thing I could possibly cross would be that green simple closed curve. If you're drawing an edge from U to A, you would have to go inside that green simple closed curve, and then you have to come back outside of it again. Okay, well, I suppose you might not cross it at all, but if you do go inside, you'd have to come out of it. So either way, a drawing of an edge from U to A would involve an even number of crossings. Now, if you look at the middle picture, you imagine drawing an edge from U to B. The only thing you could cross, again, is that curve in green. So if you're counting crossings involving the edge from U to B, it would have to involve an even number of crossings. Similarly, for the picture on the right, if you're looking at drawing the edge from U to C, the only possible edges that UC could cross would be the green edges. Okay, so if you add up all the crossings involving U, you're thinking it's even, except of course there's one vertex in the middle. We still have to draw an edge from U to that vertex in the middle. And you'd have to cross this green curve an odd number of times. So in total, the number of crossings in any drawing of K5 has to be odd. Well, that was pretty good. So now let's look to K6. Here I have, in effect, two drawings of K6, one using the blue edge from A to C and one using a green edge from A to C. Let's forget the blue one for a minute and just focus on the green. I have, in effect, a drawing of K6 where if you look at any four vertices, you'll get exactly one crossing. Okay, so that means it's easy to count the total number of crossings. That would be 6, choose 4. Okay, every selection of four vertices gives you a crossing. But now if you were to, instead of using the green edge AC, use the blue one, you'd be removing 3 crossings and you'd have a drawing of K6 with only 12 crossings. So that means the parity isn't unique because 15 is odd and 12 is even. Okay, so now let's look at K7. We had some success before looking at 4 vertices at a time, and I've done that here in green. So we know how many edge crossings are in this picture. It'd be 7, choose 4. But really what we want to do is look at the parity. So this green edge crossing using vertices A, C, D, and F, I really want to put it inside of a K5 because we know that a K5 has an odd number of crossings. So the green edge crossing is in a K4, but it's also in the K5 if we throw in the vertex B. It's also in the K5 if we were to throw in the vertex E. It's also in a K5 with A, C, D, F, and G. So this one edge crossing is in 3 different K5s. So if we add up all of the crossings in all of the K5s and the K7, we're really adding up 21 odd numbers, and each crossing would be counted 3 times. Okay, so in general, if you have a drawing of Kn, you play the same game. You look at K5s in the Kn, you would in effect be counting each crossing n minus 4 times. If n is odd, then n minus 4 will be odd as well. Okay, so if you look at K9, for example, you can look at the K5s and the K9 and add up all of those crossings, and when you do that, you will have added up 126 odd numbers. So the idea is that if you have any drawing of Kn, if n is odd, then the parity of the number of crossings will be the same as n choose 5. Okay, so read the paper for the bipartite version of the theorem. That was a pretty simple argument. The original argument maybe wasn't so simple. It had to be reworked. Here are the conjectures for crossing numbers of complete graphs, minimum number of crossings in any drawing, that is, and same for complete bipartite graph. The paper I want you to have a look at is joint work with Bruce Richter. It's the parity theorem for drawings of complete and complete bipartite graphs. There's a favorite quote from Turan.